back to the engineering course. I forgot the number of the course. Are there any questions from the previous lecture? So, as you, just like this lecture, that one was also recorded, but only half of the lecture. The second half is not good. So I will upload the first half of the lecture. The second half is Bet's limit or Bet's law of derivation, and there is exactly the same video on my YouTube channel. So I'll put the link into it so you can go there and watch. But the first part actually that is not on my YouTube channel is recorded, so you can follow that if you. Hopefully it will work properly today. If not, that guy over there is to blame. So today we are going to talk about natural hazard modeling, and I will first a little bit discuss that topic in general terms, and then I will, through PowerPoint presentation later, show you how that was applied in some of my research recently and 5-10 years ago, okay? Because if person talks just abstractly, sometimes you cannot connect that theory with how to use it. So I'll try to talk a little bit about theory, and then I'll show you how I used it in my students in some of the research. So anybody has idea what is natural hazard modeling and what that represents? No? So generally, at least in my field, but also in engineering field, there are two types of modeling approaches generally. One is physical modeling, where, for example, in my field, you have wind tunnel and you blow wind. Matthias talked about it, and you will visit wind tunnel, he told me. You put the structure, you blow wind, and you analyze what's going to happen. The other option is to do numerical modeling, where you use, for example, computational fluid dynamics, CFD models, and then you analyze how wind affects structures and so on. And similar applies to different other regions of engineering. You can have physical piece of concrete that you destroy in a laboratory, and you analyze stiffness or elasticity and something like that. And you can also do it numerically. However, it's very difficult to do thousands of these experiments. So the question is, how do we do few experiments, either physical or these very precise numerical, and then try to generalize these results to what would happen if we did 1,000 or 10,000 or million? And that's usually approach in natural hazard modeling, where we use the so-called Monte Carlo theory. So Monte Carlo theory requires some data from observations. You have to have enough data from observations, and then you generalize those data using random numbers, okay? So, for example, how many of you are familiar with statistical distributions and probability and stuff like that, right? So you had some sort of statistics. So you know what is probability density function, what is cumulative distribution function, and so on. But, so Monte Carlo modeling is a process through which we generate, do you want to ask something? No. Process through which we generate random numbers, but, and very important but, these random numbers have to follow some distribution. They cannot be purely random. For example, I can come up with numbers 1. Who is the student that gave me this? -5 points. In today's day and age, you always have to say I'm keeping, otherwise they sue you. So numbers 1, 2, pi, minus I, square root of 3, and so on. These are for sure random numbers, but to my knowledge, they don't represent anything in nature. So we can call them maybe Professor Romanich numbers, but they are useless numbers. So if you pick some numbers from here, they're not going to represent anything, okay? But if you have some statistical distribution, and here is variable x, and here is probability density function f of x, and that probability density function perhaps looks like this, like Weibull distribution that you, I think, studied, Matthias mentioned. And you generate numbers such that when you plot probability density distribution, it has same shape or very similar shape as the theoretical probability density distribution. An easier, so in Monte Carlo modeling, you have to have data. You have to have data, or you start generating some nonsense. And those data, again, come from measurement. It can be, of course, it can be field measurements. For example, you put accelerometer on a real building and you measure something, or you model that in wind tunnel, or you do it numerically. Whatever it is, you have that source of data, but you measured for 1 year and you wanna generalize that for next 30 years. You construct probability density function from this data, and then you can generate random numbers that will, when plotted like this, that will replicate your PDF, namely probability density function. Another, now where does randomness come into? So, how should I, let's say, here is, well, here is Quebec. I know it's not square, but for the purpose of this, it can be square. And Quebec per year gets between 25 and 30, 35, let's say, thunderstorm days per year. Okay, and most of these thunderstorms are south-southwest border of Quebec, not that many in the north. So let's say we have measurements, and the measurements for several years, I don't know, go like this. This is where thunderstorms occur, okay? Who are, can I have 2 volunteers that will come in front of the blackboard? Can I have 2 people to come, if nobody, if you are comfortable with that? Nobody? You? 1, okay, 2. So, take that marker that doesn't work, but it works good enough. So you will be number 2, she's number 1, she's lazy. So you, no, you take my mark. So replicate this figure over here. This one. Yes, the one that I plotted over here. Replicate to the best of your knowledge. Perfect, just the way I want it. Thank you. Thank you very much.
Yeah.
Thank you. So, this is Monte Carlo model. You see, there is one reality. This was measured. This is, I don't know the English word, I'll call it replica. Replica 1. Replica 2. Everybody, I think, everybody will agree the 2 of them captured pretty properly spatial distribution. So if you see, in both cases, there is clustering of events along the southern border, not so many events along the north border, and something in between in these mid-latitudes, okay? But none of these is the same as this one. So this is also important. So you see, in this case, it was maybe just one dimension. In this case, it's spatial, so you have to have distribution for space. But if you trust your measurements, then the claim is that if the history repeated itself, this scenario is equally likely at that scenario, and this scenario is equally likely at that scenario. In other words, it happened that we lived in this timeline where this happened, but we trust our measurements, and due to randomness of physical processes, this could have happened just as well, or this. And now you can generalize this to 10,000 samples or replica, and you'll get Monte Carlo simulation. So in Monte Carlo simulation, the first is, it's not part of Monte Carlo simulation, but it's prerequisite to have measurements. And measurements that you trust, that are trustworthy, that you believe are good. If there are some bad data in measurements, make sure you discard them or you correct them or something. And then from measurements, construct statistical distribution. And then generate random numbers that follow that statistical distribution. Now, in this lecture, I'm not going to talk now about coding, how random number generators work. You can take statistics course, and most of today's, I don't know what you're using, MATLAB, Python, the one that you use, whatever you use, these codes today, they have functions that you can use. So there is no need for you to write code how random numbers are generated. But there is need for you to know what is the process, how you do stuff, okay? And then what is the benefit? Why would we do something like this? What's the benefit of having 10,000 of these realizations compared to this one realization? Well, the benefit is here you cannot examine any variability of what will happen. In principle, these types of analysis are usually conducted for application, not so much always for research. You're not going to discover perhaps new law of physics. But you want to, you're an insurance company, and you want to prescribe, how it's called, well, how much you will charge people to insure a roof in Montreal. Well, you want to know how often roofs will be damaged due to hail, okay? But you have only that many years of measurements. And then you construct model in which you will characterize in this same way properties of typical roofs in Montreal, and you will characterize in this way how often you have hail, and then you combine these two pieces of information, and you can do 10,000 years of simulation what will happen if hail hits average building in Montreal. And then based on that, you can sort out what are the worst case losses that you will have. If the year is so bad, then your insurance company will have to pay that much to people. If the year is very good, for example, in Montreal, here we have 1 to 2 hail days per year. So you can then sort out if the year is very good, how much you will, well, you will not pay anything, so how much you will earn. Okay, so you can plan your business, and then consequently you can say, okay, I think it makes sense to charge people, I don't know, $50 per month for the insurance of, against this hazard. Does that make sense? Which you wouldn't be able to do if you have only 1 year of measurements, and you don't make use of them beyond that one particular year. So in other words, what I just described with this example is you can use these types of analysis to do risk assessment. Now, risk can be quantified, and risk is quantified as hazard times exposure times vulnerability. Okay, so we will spend some time now to examine these three. Risk is hazard times exposure times vulnerability. I come from atmospheric sciences, so we will apply this to some atmospheric phenomenon, and this is an engineering course, so we can talk about some severe wind. So how to quantify risk in case of severe wind? So first of all, you have to identify what type of severe wind you are looking into. Is it tornadoes? Is it downbursts? Is it the so-called, I think Matthias talked about, synoptic scale winds associated with mid-latitude cyclones? Is it hurricanes? So you need to quantify your hazard. And in terms of quantifying your hazard, you need to quantify typically annual occurrence frequency, we call frequency of occurrence, FOO. How often this happens in a year? Annual frequency of occurrence. Okay? Then you have to quantify physical dimensions, size. Okay? All this comes from measurements. Then you need to quantify intensity. And you need to quantify spatial extent. Where is it? Where it's usually these extreme winds? Is it here, there, over there? What is their spatial distribution? And maybe a few other things. Let's see. So I did this type of analysis, as you will see later in my slides, several times for tornadoes. So for tornadoes, I did it for Oklahoma and Kansas in the United States, and I also did it for Germany. So you go to meteorological database and you see over the last, as many data as you have, 20, 30, 40 years, how many tornadoes you have per year. Okay? Because some year was more active, some year was less active. So you will see how many tornadoes you have per year. So if you plot that, you will get some histogram. So you first plot histogram, you get something like this. So what is x-axis? Number of tornadoes per year. What is y-axis? Relative frequency, or you can just plot pure occurrence. Okay? So let's say on average, you have most often 50 tornadoes per year. I forgot now, we'll see later. I think something like this was for Germany. And this is sorry, this is number of tornadoes, this is how many times it happened. So number of tornadoes. And this is how many times it happened in your database, okay? So if you had 20 years, maybe 5 times it happened like this, once it was less, and so on. So when you sum all these in the histogram, you should get total number of events in your database. Or you can give relative frequency, that's number in each bar divided by the total number of events, okay? So this is frequency or occurrence. One more time, what's the difference? Occurrence is how many years had this number of tornadoes in them. That's occurrence. Or frequency is when you divide it with the total number. Okay? And then this is empirical histogram. So you have to find distribution that will fit this. Now, how do you find distribution? You either figure it out on your own, having your engineering, mathematical knowledge, you can guess what types of distributions would fit it, or you go and you do literature research, and most likely somebody already did it. And somebody did it. We know for tornadoes it's negative binomial distribution that properly fits this data. But we go here, it's absolutely, so we did measurements, not us. Meteorological service did measurements. We constructed, okay, empirical histogram and then statistical distribution, and then we can do sampling. So random sampling that we say, okay, some year I get 2 tornadoes, some year 5, whatever is the most often number, okay? So when you plot all these years, you should get similar statistical distribution that you got from your measurements. Size, absolutely the same. These people that measure tornadoes, observe tornadoes, they know, hopefully, what was the length of a path of a tornado, okay? This is where tornado started moving in this direction, so they know the length of the path, and they know the width of the path, okay? Different tornadoes have different sizes. So you have to connect size with intensity. Now, I don't know if Professor Bezerbeck talked, tornadoes in terms of intensity. Tornadoes are categorized from EF0, EF1, all the way to EF5. These are the weakest tornadoes, somewhat stronger, EF. The strongest tornadoes, okay? So when you connect this information, so things get more complicated. If you, for example, EF1 tornadoes have their typical size and they have their typical annual occurrence, okay? We don't just say any tornado, you have to connect it in intensity. So EF tornadoes are, let's say, smaller than EF5 tornadoes. And that has to be quantified through some measurements that you can trust. And then again, spatial extent then. Spatial, let's just put location. Where do they occur typically? Are they typically above southern border, northern border of your country, and so on? Does this make sense? How we combine this information? So that's quantifying hazard, okay? Now you can immediately see if any of these is 0, although you don't know what these maybe are, I'll explain now, risk is 0. If you are calculating risk against tornadoes and you are sure there is not going to be any tornado, then there is no risk, okay, 0. Any questions about this? So I would like you to remember that hazard has spatial, temporal characteristics and intensity characteristics. Spatial and temporal usually come directly from measurements. Intensity comes from measurements, but sometimes you also sometimes have to invoke some physical model perhaps to measure that intensity, to represent that intensity better. And I plotted one histogram and one distribution that is plotting histogram for the annual number of tornadoes, but each of these will have its own associated histogram. Okay. How about exposure? Anybody knows what is exposure? Exposure is your infrastructure, your property for which you want to assess risk. So exposure can be buildings. But this is all just, you see, devil is in the detail. Just when we said hazard, and hazard has so many properties, when we say buildings, you have to be more precise. Are you looking into high-rise buildings? Are you looking into low-rise buildings? Are you looking into residential houses? Are you looking into garage, shopping malls, or whatever? Because you have to quantify exposure. What do I mean by that? If we go back to this, so this is Quebec, exposure is usually map. Now, this is Quebec, but you want to analyze the risk to high-rise buildings, to whatever, due to tornadoes. Well, this is map of Quebec, but high-rise buildings, I mean, are here in downtown Montreal. High-rise buildings are in Quebec, I don't know now, Quebec City, sorry. And there are a few other places, okay, that have high-rise buildings. The rest of the map has exposure 0. Maybe there is farm over here, maybe there is low-rise building, maybe there is gas station, but that's not your exposure. So you are only providing map of what you are interested in. And usually, in terms of hazard modeling, exposure is the easiest part, because usually we have pretty good information where the infrastructure is, whatever that infrastructure is. And it's much less uncertain compared to typical size of a tornado path or annual frequency of tornadoes. Because it's very likely, for example, I could talk until tomorrow, it's very likely you missed some tornadoes in your measurements. Not very likely, almost certain that some tornadoes stayed unnoticed. They happened over some agricultural or forest area, nobody saw them, and you didn't account for them. That means your analysis is not proper. But what can you do? But it's not very likely that somebody will miss high-rise building somewhere, okay? So this is usually the easiest part of analysis. Yes?
I'm doing a research, I'm assuming a new configuration or a new building system, so I want to do risk assessment for this new system. So how can I model the exposure and it's still new?
For which system? For you?
But yeah, I have new system.
So yes, quite often this is good. Quite often, if I understand correctly, maybe you want to analyze exposure for city of Montreal 20 years from now. Then you have two options. One, you go to city of Montreal and say, do you have maps how you think city of Montreal will look like 20 years ago? If they say no, then you make your best guess. And you state in your analysis that this is through whatever available evidence that you believe concentration of high-rise buildings in Montreal will be 5 times more than now, and they will be, you can go wild. You can say black one are existing, blue one are the one that I think will be added, and then when you do your final analysis for risk, you can say the risk on the existing buildings is such, and risk on the planned buildings is such, and so on. Make sense? I will actually show later in results part one example where we did exactly that for wind turbines, not for buildings. Any other question? Okay, so that's exposure. Now it is very clear also that if exposure is 0, there is no risk. If tornado, again I am attaching this to tornadoes, but you are intelligent to understand that it can be applied to any natural hazard. Earthquakes as well, not just atmospheric science. But if you have tornado over water, which is called water spout, but if you have tornado over water, clearly exposure for high-rise buildings is 0, because there is no high-rise building over water. So from your point of view, there is nothing to worry about. But if you are measuring, if you are quantifying risk for boats and ships, well, then exposure is not 0. And the last part in this analysis is vulnerability. And this is the most uncertain and most complicated part. Conceptually, it's very simple when you make some assumptions, but the most uncertain part of this whole modeling business is vulnerability. Anybody knows what is vulnerability?
Like a fragility?
Similar, yeah. So vulnerability is, well, maybe I make it bigger. Vulnerability, before I plot everything, is how well, vulnerable, how susceptible this exposure, this building, is to particular hazard, okay? So for example, if you are analyzing how tornadoes affect vehicles, and one exposure is, and you have different types of cars, okay? So you lump all these cars under the same exposure. You don't now make exposure, these are Jeep cars, these are Toyotas. You say all cars are the same. So exposure is all cars are the same. But really they are not the same. They are not the same. They are aerodynamically a little bit different, they have different masses, different size, and so on. And therefore, the same hazard will affect differently different cars. And that can be quantified through vulnerability. Another, even better example, I think, as I was speaking, I thought about, let's say you have identically same exposure. You have high-rise building. Here is surface of the earth, here is high-rise building. Or from the top view, this is the cross-sectional area of your high-rise building, which for this analysis is more important. So you have a tornado approach, or strong wind approaching from this direction. Is absolutely not the same as approaching from this direction. I'm sure you studied in this course corner separation, corner vortices, and whatnot. And if this building is a little bit actually elevated, if it is not perfect square, then this is not the same as coming from here, okay? So you have same exposure, but you have natural variability in approach angle of your hazard. That means this building will differently respond. Maybe you will have not so much damage, a lot of damage, something in between. So, for vulnerability, x-axis is intensity of the hazard. In case of tornadoes, and this is wind engineering course, it will be wind speed, let's say in meters per second. Now, wind speed, again, you have to, what is wind speed? Wind gust, 1 minute wind, 3 second wind, whatever it is. But some quantification of intensity. And y-axis is usually called damage index, which is non-dimensional parameter. What would be damage index? Damage index is index that quantifies how much damage your exposure sustained for a given intensity of hazard. So if you have, and this damage index goes from 0 to 1, it will be clear when I plot it. If you have very weak winds, like outside right now, well, there is no damage. So damage index is 0. So usually you don't have any damage, and then damage starts occurring, and you plateau. Just like power curve. You remember from wind turbines last time? Because if you have high-rise building and you destroy entire building, you cannot destroy it more than destroying it. So if this tornado destroyed entire building, well, the stronger one will just equally destroy it. Very weak tornado is not going to do anything. So we would say perhaps these are EF0. Maybe EF0 are weak. Matthias talked. EF0, for example, is wind gust between 29 and 39 meters per second. So not so crazy tornadoes. So probably if you have good building, it will not be damaged. But if you have some poor old tower, maybe it's going to. So vulnerability curves are a function of your structure. And then you start having EF1. And then EF2. And then let's call EF3 plus. Again, I know that some of you probably are not familiar with EF scale that much, but study a little bit later on your own. I know that Matthias introduced it in one of the previous lectures as a scale to measure intensity of tornadoes. Now, here is another important thing to note. When we do this modeling, People are always, wow, if you have EF5 tornado, the strongest tornado ever, we actually don't care that much about that tornado. Because we know it will destroy everything, and there is not much you can do. But fortunately, it will happen once in 10,000 years over a given region. EF0 are problematic because they are very frequent. They are very frequent, but they are weak, so not much damage will probably be occurred. But the biggest headache are these intermediate ones that are strong enough to cause damage, either partial or total collapse, and yet they are still relatively frequent, okay? So that's what you usually see in results, that your results are most susceptible on how good your data are at representing these intermediate range hazards in general. Again, if you have very weak earthquake, nobody cares, but whatever, it's not going to be that much damage. If you have the strongest earthquake ever, well, it will just destroy everything. But those in between are the ones that matter, and how you model damage of those intermediate ones. And the same goes for hail, for strong winds, for whatever. So you see, people used, when COVID-19 pandemic came along, immediately people jumped on board. If I was smart enough, probably I should do it. Would be famous now. But people did the same analysis for COVID-19 pandemic. So what would be hazard exposure vulnerability if you had to model propagation or propagation of a virus through whatever, classroom or something like that? If you have a classroom full of people, what would be hazard, what would be exposure, what would be vulnerability to a virus? I claim that hazard could be people. So, first of all, hazard is people. Now, if this virus can affect, like COVID-19, they said it can affect deers, those animals report is that deer. So, if you want to do both, then hazard could also be some animals. But in this case, hazard is people. Now, you could subdivide it. You could say hazard is you're only looking into men or women. So that's your hazard. Sorry, you see, I made a mistake. That would be exposure. Hazard is virus, sorry. Hazard is virus. Hazard is virus, how concentration of that virus, for how long it stays in this room. Okay, that would be hazard. Exposure would be people, sorry. And what would be vulnerability?
Like the age, the health history of the person. So.
Yeah. Now, usually age, you would put an exposure here. But I would say vulnerability, which is the most uncertain part, is everybody has different immune system. So somebody with the same amount of virus, you and I get sick, you don't get sick. Why? Nobody knows. He has better immune system. So we end up with something that is vulnerability. So how do we get these curves, vulnerability curves? Any idea?
You sample large amount of patients, how they respond.
That's correct. That would be correct in the case of viruses or some diseases. But in the case of, if we go now back to wind engineering, and I don't know, hurricanes, tornadoes, whatever you want, you do measurements. Again, probably not that you will do all of this, but you get measurements from someone. And what would measurements be for in this case? These are called forensic. I think Professor Bezovic also talked about this. These are forensic analysis. Historically, tornadoes passed through urban areas. They caused damage. And you knew what was the intensity of the tornado, you know damage. And you plot your data. And then through this data, you fit a curve. Okay? Now, in case of damage index, these have to be like a cumulative distribution function curve. With the increase of intensity, you have to have increase of damage. They have to be monotonically increasing. Okay? Or rather, better to say non-decreasing. They could be constant like this. You see, this is no longer increasing, but they cannot they have to be non-decreasing function. So you did, over the last 20 years, EF tornadoes passed over your exposure, high-rise building, and you have these data. EF2, you have these data. EF3, you have these data. Usually reality is never so clean, so your data usually have a much bigger spread. And that's what I want to emphasize. For vulnerability, you have much bigger uncertainty than for anything else. That's because there is so much natural variability that can happen, and you cannot quantify all of these. In principle, you could say, I'm only going to look into tornadoes that approach buildings from corner. But then when you go back to your measurements, you will figure out you only have 5 data points. So you cannot construct this analysis. So you have to look into all tornadoes, but all of them affected buildings from different approach. What would be another measure of uncertainty here? How maintained is this building? You have 2 same buildings. One is, let's say, 10 years old, another one is 50 years old. Or you have 2 same buildings, 50 years old, but completely different level of maintenance. Or you have 2 same buildings by look, but one is designed by code, another one is not designed by code. So all these are natural variabilities that end up being lumped into this vulnerability function. Okay? Is this clear? Any questions? So at the end, in the last slide, I completely non-mandatory, but I put together steps that you can pursue, and you can get your own Monte Carlo analysis. So I provided link, for example, for tornadoes data in the United States. I told you what you can do, and then it's just one step, it's this. So you can generate annual, you can plot histogram of the annual number of tornadoes. I think I did it for Oklahoma. And then you can create your Monte Carlo simulation and compare your histogram against measurements. And when you do that, everything else is just copy-paste, whether you are doing length, width, intensity, and so on. Okay? Yes?
Question? So, when we have measurements, right, so we take the statistical properties, and then we construct millions of simulations. That is what we're assuming the process or the loads, they're stationary.
Yeah.
The statistical properties, they're the same. But let's see, if with the global warming or climate change, you have a change of the wind load, snow load, or even wind load.
Yeah.
So the future 20 years, they could be different from the last 20 years.
Yeah.
So in which part of the equation should we address this?
So generally, so there are 2, in this way, we do not do it. We do not address it. Because when you, this is a good question. When you are generating 10,000 years, you're not generating 10,000 years in the future. Each of these 10,000 years, you're saying could be next year. Now, next year could be very quiet in terms of tornadoes, but it might be very violent. And you, in these 10,000 years of simulations, you're exploring all spectrum of possibilities. And then based on that, you make decision, whatever that decision is. But you could, just similar to his way, you could do it also for future projections. You could say, I will generate 10,000 realizations of years in the current climate. And then from some, now you cannot, this is also, you cannot go to measurements to see what will happen in 2050. You have to take data from some climate model. And you say, based on the data in my climate model or whatever your source of data is, I noticed that tornadoes will be longer. I don't know now. Everything else being the same. And then you incorporate that into model, you run 10,000 years and you compare. And you say, okay, this is my current climate condition, and these 10,000 simulations for the future climate projection look like that. Does that make sense? And also, yes, go ahead.
If we were dealing with more than one hazard, or if it's more of like a multi-hazard analysis, what would be like the general way of approaching it?
You can have multiple hazards here. You can have hazard 1 times hazards 2, but then you have to have multiple vulnerabilities. You can also lump different exposures. Just like when he said what happens if you have future buildings, right? So you have black current buildings, blue future buildings. So you could have different exposures, different hazards here, and then later in your results you disentangle which hazard caused particular damage. Now that's if these hazards are statistically independent, right? But if they are statistically dependent, like for example, hail and wind can be statistically dependent, then it gets more complicated. Then you have to know the so-called joint probability function of hail occurring with strong wind. Or sometimes also hail occurs with tornadoes. And you say, oh, I want to analyze this particular situation. Then you are, I mean, it's more advanced, but you're in trouble because usually you don't have good data to quantify what is the joint probability of hail and tornado. And then also you end up in trouble because you have now in literature, you have vulnerability curve for tornadoes. You have vulnerability curve for hail. But for two of them together, it doesn't mean it's linear combination of these two curves. So it's something else. Does that make sense? So short answer is you introduce joint probability function, but the long answer is it's not that easy because we usually lack data to couple multiple statistical variables like that. What I wanted to say is to conclude with, I hope you understood, if hazard is zero, risk is zero. If exposure is zero, risk is zero. Well, if vulnerability is zero, risk is zero, okay? Okay. And also, it's very important to understand that vulnerability is function of your exposure. You will have one vulnerability function for wooden buildings, wooden structures. You will have another vulnerability function for brick or some other material, okay? And this is why, and there are not that many buildings out, wooden buildings, let's say wood, mid-rise wood buildings. How many is out there? Not many. And you want to analyze how tornado will affect it. Well, how are you going to construct vulnerability? You know how many tornadoes. You know where these few buildings are. But historically, how many tornadoes affected wooden buildings? Not that many. And then you have big uncertainty in your vulnerability curve. This is why also when you do this research, you will notice that the researchers, but particularly firms like insurance companies, they will never share this with you because they are so jealous. The insurance companies, they have a lot of debt. I mean, their business is damaged. So they have a lot of this data and they construct these curves, and based on these curves they can prescribe how much they will charge people. But they don't want to share it because they don't want other insurance companies, or maybe you open an insurance company tomorrow in their neighborhood, so they don't want you to know this. Does that make sense? Anybody watch Simpsons? Simpsons TV show. There is one episode, and something happened, I don't know, an insurance dealt with it, some hazard happened. And then somebody said, I forgot who, let's say Homer, said, but imagine a world without insurance companies. And then the next scene is just like heaven. And everybody is singing and they're happy and so on. I have to make sure to remove this from video. Otherwise, my car insurance will go 100% next year. Okay, actually there is not much more I wanted to say. Any questions? We have 30 more minutes, right? Yeah. Any questions about this? So this is very satisfying analysis, to be honest. This is very simple. And I encourage you, and it's applicable to whatever you're doing as a researcher. Again, hazard, exposure, vulnerability can be applied to anything. Lastly, so anyways, to finish, if you have opportunity, do these analyses, and you will learn a lot in terms of risk and planning if you want to plan something and whatnot. Lastly, we can calculate losses from here. Loss is when you multiply this with money. Because you came all the way to this point, and you know that, let's say, for a given EF2 tornado, your damage index is 0.6, so just it's not 0.5. So let's say 0.6 is damage index. In principle, this would mean 60% of your house is destroyed. Now you have to attach money. How much it costs to repair 60% of your house? I mean of your house, of a house. Okay? Quite often, you see, when you start with vulnerability, you can have damage index 0.9. That's perfectly fine number, or 0.99. But when you go to calculating losses and you attach monetary value to these things, then this is at least my rule of thumb. Anything above 0.7 is 1. Because if you have a building that is 0.99% destroyed, well, that's exactly. You're not gonna repair that. You will just destroy everything, and you will assign monetary value that is building new building, okay, constructing new building. Whereas if the damage is here 0.2, okay, that's 20%, and that's maybe a roof. Okay, so you will fix roof, okay, and you don't have to replace entire building. Did Matthias talk about degrees of damage? I think he did, right? So this is the concept of degrees of damage. If you have a tornado and tornado passes over this particular building, very little damage, that means some pieces of cladding and so on. That's usually called DOD 0 or DOD 1. So that means usually it's defined as a threshold of visible damage, few spots damaged. Then you have DOD 1. That's, for example, I don't know now, 20% of the roof damaged. Then you have DOD 2, whole roof damaged and so on. So these degrees of damage are also a function of structure. Simpler structures, like I worked with luminary masts or lighting poles, they have only 3 degrees of damage. DOD 0 is the threshold of visible damage. That's like maybe just that lamp broken. DOD 1 is bent pole, and DOD 2 is collapsed pole. But if you have building, which is complicated structure, it's not that simple. You usually have 10 degrees of damage. Partial damage, roof blown off, 1 internal wall, 2 internal walls, and so on. Okay? So we get loss by multiplying this. So damage, what is difference damage and loss? Damage is structural damage, something is damaged. Loss is when you assign monetary value to that damage. Okay? Any questions? I don't know if anybody can see cap. No. So let me show you a few results that I and my student did in past using this approach. Do you want to shut down the system? So here are, this is so awkward. So here are 2 papers I started with. So Oklahoma tornado risk and variability. So we did this analysis for Oklahoma, and later we generalized it to Kansas, but not just Kansas, we also improved. What did we improve? For example, we improved the representation of hazard, we improved the representation of exposure. And then most recently, my undergraduate student and I did Monte Carlo modeling of tornado hazard to wind turbines in Germany. So in the title you already see the hazard is tornadoes, exposure is wind turbines in Germany, and what about vulnerability curve? Well, I'm also very proud to say that in that research we proposed the first, which I will show, the first vulnerability curve for wind turbines affected by tornadoes. So what was, for example, methodology in this 2023 paper was the same as methodology in my original paper, 2016. So namely, we have hazard, annual frequency, and different properties of tornadoes, intensity, length, width, just as I portrayed there. And this is where we got data. Where did we get data from? Tornado database. National Severe Storm Laboratory in the United States freely provides those data. Exposure map, official United States data for exposure. Here we looked into 1 and 2 family residential buildings. So you have 1 and 2 family residential building map in Oklahoma. And vulnerability curve, we took it from literature. Some people already investigated how tornadoes affect these types of buildings, so we just took that from literature. So that's also what I said. Usually it's not you doing these measurements, these, You collect data from people that already did those measurements. If something doesn't exist, then you try maybe to gather your own measurements. So here is annual number of tornadoes. So typically you see we have around 26, 30 tornadoes in a year, and in our database we have 40 years, so that happened 40 times in that 40 years. And we fitted empirical distribution with probability. Very important, is fit perfect? No, it's not perfect. But we are assuming, this is also known as theory of large numbers. We are assuming the more and more and more and more data you had, the closer blue histogram, which is empirical histogram, would be the theoretical negative binomial distribution. Okay? So here is exposure. One representation of exposure here expressed in population per square kilometer living in those 1 and 2 family residential buildings. And here is vulnerability curve for EF1. This is old scale F1. EF stands for enhanced Fujita scale, and then in 1990, I believe you saw, it was enhanced, or 2007 rather, it was updated to enhanced Fujita scale. But I would like to, last few slides, devote to this most recent research that we did in Germany. So what do we have? Here's x-axis is years, from 1970 to 2020 in that time. Annual number of tornadoes occurred. So you see, typically we get 50 tornadoes per year. And that happened in about 9 times in this time period. Okay? And then again we use the same curve. Negative binomial distribution. Why? Because other researchers demonstrated that it's not perfect, but it's better than many other statistical distributions. And now you're in the business. You can generate, you go to MATLAB, Python, whatever you use, and you say, okay, generate random numbers following that distribution. And that distribution has particular parameters, shape parameters, that you get from empirical data. I'm not going into it, but you use maximum likelihood method, you use different methods to estimate parameters of your distribution from data, from empirical histogram. Tornado track. This is something I omitted. Usually, tornadoes, when they form, they are a little bit weak, and they strengthen, and then they dissipate. So you can see that you have evolution of this tornado. So EF3 is classification of, how should I say, tornadoes are classified based on their strongest intensity. But EF3 was only this portion of the total time. So this is also, this is usually when you code, this is complicated to code, but from other research, people figured out, if tornado is EF3, then only 20% is EF3. This over here was EF1. This over here was EF2. Now you might ask me, how much? Because when you get data from meteorological service, they tell you this length, they tell you this width. Basically, they say tornado started in Montreal with this diameter and ended up 10 kilometers north of Montreal. So how do you determine these small patches? Well, either you know it from your own research, but fortunately there are